Welcome to Safety Engineering Briefings. Short, practical insights for software and security engineers. Think about a bridge. A beautifully engineered bridge. We celebrate its strength, its capacity. But the first thing engineers consider isn't how much weight it can hold. It's how it behaves when approaching its limit. What happens before it collapses? That's where the real engineering happens. We don't design for the ideal case. We design for the inevitable deviations from it. This applies directly to the systems we build. We spend too much time optimizing for success and not enough anticipating what happens when things go wrong. We naturally focus on positive paths, happy paths, successful transactions. But systems are rarely static. They're constantly bombarded with unexpected inputs, resource constraints, and external pressures. Consider a simple mechanical switch. It's designed to connect a circuit. But what happens if someone applies excessive force? What if corrosion builds up on the contacts? What if the spring loses tension? These aren't edge cases. They're predictable degradations. A common misconception is that robustness means handling any input. It doesn't. It means understanding the range of plausible inputs and designing graceful degradation within that range. It's about defining clear boundaries. What is acceptable? What is not? And what happens when those boundaries are crossed? Think about error handling. Too often, it's an afterthought, a catch-all block at the end of a function. That's not engineering for failure. That's hoping failure doesn't happen. True engineering for failure means proactively identifying potential error conditions and designing specific responses. Not just logging an error, but preventing cascading failures, limiting the blast radius, maintaining a safe state. Another key point. Failure isn't always dramatic. It's often subtle. A gradual increase in latency, a slight deviation in data accuracy. These are early warning signs. We need to build systems that expose these signals, not mask them. Monitoring isn't about detecting failures after they happen. It's about detecting the precursors to failure. Let's look at a simple example, an e-commerce product catalog. We have a database storing product information, an API serving that information to the website, and a caching layer to improve performance. A common failure mode is database overload. Maybe a marketing campaign drives a sudden spike in traffic, or a faulty query causes a full table scan. If we've engineered for success only, the database will become unresponsive. The API will start timing out. The website will crash. Customers can't buy anything. A classic cascading failure. But if we've engineered for failure, we've anticipated this. We've implemented circuit breakers in the API. When the database response time exceeds a threshold, the circuit breaker trips, preventing further requests from reaching the overloaded database. We've configured the cache to aggressively expire stale data, reducing the load. We've set up alerts to notify the operations team. The website might become slightly slower, but it remains functional. Customers can still browse and purchase products. The impact is contained. The system degrades gracefully. Don't design systems to simply work. Design them to fail predictably and safely. Understand the likely modes of failure and build in mechanisms to detect, contain, and recover from them. What single point of failure in your current system worries you the most? If this topic was useful, take a moment to reflect on how it applies to your own systems. See you in the next briefing.